Okay, so in this video, we'll be going over well, in this particular video, we'll be going over the theory for extending our discussion of linear impulse and momentum from previously to on particles to now we're extending it to rigid bodies in planar motion, and just a brief recap of where we are. Right, we first started with particles, looking at the kinematics and kinetics for particles, and then we extended that. Have now been extending it for a while here to rigid bodies in planar motion, and that planar motions means that we can always describe all of the motions on some plane, and so points on a plane stay in that plane, but move around in that plane, and that required a lot of discussion of rotation and rotational kinetics, and so this is really the last topic of that, right? So we will be talking about the idea of momentum, and that'll allow us to do some analysis of collisions. And then the last thing, all that we have left in the class after this to talk about is true 3D kinetics, 3D dynamics, and excuse me. So, and then that will wrap it up, okay? But in the short term, we'll talk about this in this video. Won't actually be too much to discuss. I'll go over a brief example, and then we'll talk about impacts, and then have some examples in the coming videos. Okay, so we're going to start with just some reminders of aspects relating to momentum that we've talked about in the past. So we started by defining what the dynamical property of linear momentum is. Okay, and that is a vector quantity. And for a rigid body, right, it's its mass times the velocity of the center of mass. Where and then we can define the motion of individual points on the body separately, and that involves talking about the angular momentum. Again, still a review, nothing new here. This is now we give a few different symbols, but basically h is our angular momentum symbol. It is also a vector, and this is now the angular momentum about a point O. And we have to, with all these rotational things, there has to be a point in which we are taking rotations about or doing a moment about, right? And that now we can relate to the center of mass through, so the angular momentum about some point O is the angular momentum about the center of mass. And then we got the position vector crossed into the linear momentum. So it's the linear momentum of our center of mass with the position vector relative g to O crossed into it. Okay. Our so this term here. So one of these special cases was this. This is now so we actually have two special cases. So we have now planar motion for both of what follows, and this one here is about the center of the mass center. Okay, and then the one below it is going to be about a fixed point O. And that looks like this. And so all that we've done with these two different definitions, right, is a different moment of inertia point in which we are, taking the moment of inertia about. Remember, now these are resistances to rotation, right? So there's no forcing going on here. There's no kinetics yet here. In fact, this is mostly, we're leading to kinetics here, but it's really just a description of motion still, right, where we have the translational velocities and the rotational velocities. So let's get into the true kinetics part, which is where we actually talk about the forces and the moments involved. So in particles, we talked about linear impulse and momentum, but linear, okay? So not no angular, because we didn't, well, we introduced angular momentum back then, but we didn't have much to say in terms of the momentum for collisions didn't get much affected by angular momentum. We focus more on linear momentum. All right, so so our impulse is the accumulation of force over time, and that equaled the change in momentum. And so what we had is that, well, if basically the left-hand side could be assumed to be 0, or was 0, shown to be 0, and that would be the case where there are no external forces. Maybe there's no net external force. And so oftentimes this is applied, we get this from applying it to a system of particles, which then allows us to relate the velocities before and after a collision. Because, if there's no, we could, if there's no external forces on an object or a particle, with a single particle, right? Then it might be an interesting kinematics question, right? Like how does it move through space? But if there's no external forces, then there's not a lot interesting beyond a kinematics problem going on. It's not really a true dynamics problem. But if we apply it to a system of particles, then there is some dynamics going on. Is that the two particles could be colliding with one another. They could be having a force on each other. And now we have a kinetics part in that there's two forces on each other. But to the system, there's no external forces, but each one has a force on itself. And so momentum really is then a way to then say, okay, even though there's no net external forces on two particles as they collide, excuse me, this then allows us to relate their velocities before and after a collision. All right. The other thing we talked about was how linear impulsive forces that are, it's related to what I said here, that are internal to the system. So these are could be rather violent forces of the two particles on each other. They have no effect on this analysis here. They have no effect on the entire linear momentum of the system. Okay, so that, as long as you treat the whole system in kind of maybe a tight window of the tight time window here, just right before the collision or right after the collision, then there's a lot of force on each other, the two particles. But if you treat the two particles as the system, there's no external forces. You can basically set this left-hand side to 0, and you got this equals 0. Well, now you've got the total, momentum conserved. And there might be two particles here, so you'd have terms for the two particles. But okay, all right. This is all under the. It's not even off the page or off the screen. All under the review or the recall. Okay, so this is nothing new yet. Okay, now let's get something novel here. Angular impulse. We're basically extending this last statement of linear impulse and momentum. How does this extend for angular motions? Angular impulse and momentum. Okay, and again, this is of rigid bodies, so nothing, not considering deformable bodies at all in this class, in planar motion. Okay, so we can choose a plane on which points rotate about, and okay. So if we analyze about the mass center, okay, then the extension of our impulse momentum relationship to angular is very similar. We integrate on coming back up here, right? This would be from like one time to the next time, t1 to t2. So we do the same thing down here, t1 to t2, but here we accumulate the moments about that mass center g over time between these two times, and then that should balance, well, if this is the change in linear momentum, this should balance the change in angular momentum. Okay, so let's categorize these two terms and define them. This is our angular impulse, okay, which is it's the sum of the moments, right, calculated about the center of mass on the body, and then integrated, and then whenever we integrate, right, we're accumulating things, accumulated over the integrated variable, so over time in this case. Sometimes we integrate in space, and then we're accumulating that quantity over space. This is over time. Okay, so right, so it has some temporal aspect, and then it has some accumulation aspect of the moments. That then, based on your choice of time, gives you that gives the change in the angular momentum about the center of mass again. Right, that's what's different about angular. You have to be so careful with where our point is that we're doing calculations, right? Change in angular, this then equals a change in angular momentum about the center of mass between two different states or two different times, right? All right. Okay, so then we could also do this about a fixed point. Call it O, as we've done in the past, right? And now this just means that the point itself isn't moving and helps us to... I mean, we've seen this for the work energy in another... back in when we were talking about angular momentum too, right? That showed up here in the force mass acceleration for rigid bodies. Okay, and all we're doing here is changing the O's to G's, right? So this is just everything the same. So I'll just say, identical to above, but all of our calculations, all of the moments and the rotations are about this point O. Okay. So this is kind of the theory, right, for what impulse and momentum and how they relate. We'd now like to talk about the conservation of angular momentum, like we had conservation of linear momentum that allows us to relate the velocities before and after a collision. Well, if we're going to do the exact same thing here. If we can somehow say that these two, the left-hand side here is 0. If we maybe pick a point, we're smart about our choice of a point to do the analysis on where this left-hand side is 0, then we got this powerful tool that our angular momentum is the same before and after. We can again relate, in this case we'll be relating angular velocities before and after the collision. Or before and after something happens, right? Okay, so that is the idea of the conservation of angular momentum, like we had conservation of linear momentum. Okay, and the idea here is it's different a little bit too, because we can choose a point. We can kind of impose that our analysis point is such that our sum of moments is 0. So then we don't have to do any of that accumulation through time. It just becomes a change in a change in the angular momentum. So purely a relation between angular velocities at two different states. So choose a point. This point will be O when we write it down, right, in our notation. Then we have the angular momentum about O. In state 2 is the angular momentum about O in state 1. Now, and just like with linear momentum, this may be useful for a single particle, but it's oftentimes helpful for a system of bodies, or maybe for one body. But this is actually, we can also use this for a single. This is also useful for a single body more than the linear momentum is. In that there are times that there are a lot of forces involved, but you can then there are many points where basically those forces don't contribute a moment, and if that's the case, then we will see an application of this to single particles alone, before and after a collision. They don't come always as systems of bodies. We'll see that in the examples as we go along. So for systems of bodies, right, multiple ones in contact with one another, we can only consider external moments, like we did with external forces for a conservation of linear momentum. If there are none, which is a typical occurrence, which is what we are looking for, then what we can get is initial, so there's something a lot going on here, right? This is the angular momentum about point O, so our calculation point, calculating about point O, that fixed point O, for particle, or body A, shouldn't say particle, for body A at state 1 or time 1. All right, do the same thing about O for object B at state 1. All right, so basically that, I flipped the order here. That's all of this over here. It's just now the accumulation of two bodies in a system. Same thing, but now with two. So we are just saying that no matter how we define what our system is, if we choose a point where this is true, no matter how we've defined the system, whatever is initial, or well, throughout the evolution of the system, this total angular momentum stays constant. Okay, that's just the main idea. Okay, so let's now, yeah, let me applicable to single bodies when forces do not cause moment. Again, based on a choice, and that's why I underline that, based on a choice of that O point. Okay. Right, and so obviously a good choice here. Let's have like one brief picture here. So if we have, two objects here, maybe maybe another object here, and this one's kind of heading this way, and maybe this one's heading that way, and they make contact right in the middle here, but at a point there and at a point there where they finally make contact with another. That's going to be a good point in order to put, maybe that's point P. Point P is a good choice for O, right? In that their contact where they hit each other will be, that force won't necessarily be producing a moment, and so we could actually do analysis not just for the whole system. We could actually do conservation of angular momentum for just each individual body, and that's the type of example. That's the type of system we'll have in an example in the next couple videos at some point. I just know that because I prepared that, and not sure. I think it comes in two more videos down the road. Okay, so before we get there, let's start with an example that would be an in-class demo. But we don't have the luxury of doing that here. What we'll do is hold a spinning bike wheel while sitting or standing on a rotating platform. So sitting on a rotary chair, one that has the ability to rotate, and then flip the wheel. And flip wheel. What I want to do is what happens, just kind of describe the motion in a qualitative way here. Okay, so here is, let's put a person here. We'll just represent them as standing on this platform. They could be sitting on a chair though. And again, we have the ability to actually do this. And we just need this, we need them to be holding this, this is now a bike tire, so maybe I'm going to put the treads on there. Okay, holding a bike tire kind of horizontally here, and now we got a bar going through the center that allows it to spin there. And so this, let's call the person is A, the bike tire, or the bike wheel is B. The wheel then rotates right now about this axis, right? So it'd be rotating, to have your thumb go there, it'd be kind of going into the page there, and out of the page there, right? So, okay? And so then the person is holding on to it. Okay, and let's say that they currently, let's say in this configuration we have it so that there is no rotation of the platform right now. Just so we have a place to start. So omega, oh, that shouldn't be k. Let me redefine this. This is omega b k. I don't know why I put omega k. Okay, so let's say omega a1 is then 0. Okay, so this has the ability to rotate, but it's not. Let's write these right. So this is A is a person on a rotary chair or platform. Okay, and currently has no rotational motion. And then this is a spinning bike wheel. I don't know why I keep saying tire. That's just the, the outer part. And let's label this as state 1. Okay, and then through time, well, not through time, just at a different state. See if I can match this up. Same person. Here's the platform they're standing on. That has the ability to rotate, right? And now what we've done is now they've switched their hands, kind of flip the thing over. By the way, you can feel this effect with just like a fidget spinner. Spin it in your hand, flip it over. You can feel this, the want of the system to have the effect that we're analyzing here. We're going to put the treads in the other way, right? The other orientation, and then they're holding on still. So they just kind of swapped their hands around, right? And so that means that now, and let's say it keeps its same angular velocity here, and so now omega b points downward. Here's b and here's a. What we want to do is what happens down here, right? Does this start spinning? And I'm just going to put in a direction. So this is omega a, would be really omega a, 2. Okay, so let's see here. Let's apply our, so this is state 2. Let's apply our conservation of angular momentum, because there's no actual, and we're going to ignore any friction and just apply angular momentum, okay? Conservation of angular momentum. Okay, we will choose. Okay, so this is now angular momentum for A in state 1, all coming from here. And that, it should be balanced by, so equals HOA2 plus HOB2. Okay, this first one is 0, right? Because we've assumed omega A1 is 0. No rotation there at the beginning. And then, well, let's plug everything in, right? So this would be the moment of inertia for B, omega B1 equals I moment of inertia for the person, omega A2, plus the moment of inertia of B, omega B2. Okay, well, again, we've kind of assumed that they just flipped it around and it kept its spin. So we've assumed omega B2 is just the negative version, where we've flipped over the direction of rotation, the axis direction. So their magnitudes stay the same. What happens to the person, and do they get a transfer of that? We'll talk about where did the angular momentum transfer to, and where did it come from. So in the end, IA, if we solve for this, moment of inertia omega A2 equals, well, this is just negative, pull one more to this side, because this would be negative, over to this side, we get 2IB omega B, right? Just that omega B1 is positive omega B, omega B2 is negative omega B, right? Right. Okay. So that's the final result. And what does that mean, right? And by the way, these moments of inertia, you haven't even labeled what the O axis is here, and that's just, you know, whatever, that would just affect what the moment of inertia would be. Right? Maybe it's the central axis here, right? So we could pick, you know, this point right here to be O to analyze, and then you've got the moment of inertia of the person would be its kind of mass distribution, and the wheel would have a mass distribution about that. Okay. So the way we interpret this result, right, is that, well, it looks like the momentum, the angular momentum that A has in the end comes not only from the initial angular momentum of B, but actually twice that. We have, you know, it's twice as much. And so the person now rotates with an angular momentum from the initial spinning wheel. And by the way, this is in the direction of the original one, right? That's what we got here. Whatever direction omega b was in, now omega a is in that direction, but twice as big in terms of the angular momentum as the initial, right? And the way it works here is like holding on this way and then getting it to vertical. This b would have no angular momentum about o anymore, right? Whatever that horizontal, or I guess it would be a vertical axis on the plane, right? So if you turn the wheel and go this way, that angular momentum has to go somewhere, where that angular momentum got transferred into the whole body, right? And then, you know, which would rotate it in the same way that omega b used to be rotating, or that b used to be rotating. And then to flip it this way, now you have the angular momentum going the other way, and so then there must be a balance there. There must be a conservation of angular momentum. So basically, you've turned this upward angular momentum into nothing by going vertical. Sorry, you should start like this, and then by going vertical. So now the wheel is going like this way. Now there's that angular momentum that was original has to go somewhere. That now goes into this rotation, but that would only be 1 IB omega b, and then getting all the way to horizontal, but in the other orientation. You know, now we have a negative angular momentum that must be balanced by another one of those terms here into the rotation, right, of A. So the person rotates with angular momentum from the initial spinning wheel, and to counteract or cancel the extra angular momentum given to invert the wheel and give it that negative angular momentum as we've drawn it, okay? So when I say the initial spinning wheel, this first part is only to bring B to the upright position. So it's rotating about a horizontal axis. Rotating about horizontal axis. And then we got the extra one, right? To counteract, you know, now that we have it to bring B rotating about negative vertical axis. Okay? And so in the end, right, this example, and this is where we're going to leave it here. This has positive angular momentum, because it's in about the positive vertical axis here. You know, this is contributing nothing. So the whole system just has positive, right? This one now we have the same magnitude but negative angular momentum. So this must be first cancel that and then provide us what we had originally. And that's what we mean by conservation of angular momentum. Okay, we'll come back next time, talk about impacts, and then a video to follow, which will have a more detailed example of this conservation of angular momentum on impacts.